Hello, am I audible?
Yeah.
Okay, I'll wait for 2 3 minutes. Let's others join. Okay, welcome you all for this NPTEL discussion session. This is the week number 4 session. I'm the TA of this course. I am Nikhil Gupta, which is the. I'll start today's lecture. Okay. So today's lecture is week number 4, where I'll cover the questions related to the assignment number 3, which you have already submitted, and I'll in midway I'll answer the questions which were asked in the last class, and also I'll discuss some few more questions which are helpful for solving the assignment number 4 as well. So let's start today's class. So this is the question number 1, which was of the assignment number 3. It says in finite element method, at a node of interest, the summation of shape function. So you all know that summation of ni is equals to 1, which is the property of the shape function. So how it happens, let's just say this is node 1, this is node 2. So n1 will follow this and n2 will follow this. So at this node you see 0 plus 1 is 1. At all node it will be equals to 1 only. So the answer is A. No, answer is B means 1. So the next question here is choose the correct option. In weighted residual method, the weight function does not require to satisfy the homogeneous boundary condition. And the other option is in weighted residual method, the error or residual of a system can be orthogonalized with the respect to weight function. So I write the answer. What happens in weighted residual method? The weight function does not satisfy the homogeneous boundary condition. The primary requirement is that the weight function should be linear independent. and sufficiently differentiable. To ensure residual error to be zero. So and this zero is through orthogonality condition. So if you check the answer, uh, it says weighted residual does not require, so it's correct. And the second option, it says the weighted residual can be orthogonalized with respect to weight function, so both are correct. The answer is A. Let's go up to the third question. It says let a cantilever bar is axially deformed. So with a axial load Q, the bar is discretized with 1D element with n1 and n2 as the shape functions for node 1 and 2. Length is Le and axial displacement is U as linear and coordinate system is X. If each element is approximated with linear polynomial, we have to find the n1 and n2 for that. So we know from Lagrange interpolation formula, when phi is equal to n1 phi 1, n2 phi 2, n3 phi 3, go up to nn phi n. So finding n1, we have the formula as x2 minus x, then x3 minus x, and so on till xn minus x divided by x2 minus x1, x3 minus x1, and go up to xn minus x1. Similarly for n2, we say x2, not x2 here, we'll write x1 minus x, then x3 minus x, go up to xn minus x divided by x1 minus x1 x2, then x3 minus x2, go up to xn minus x2. So there is a pattern in this for which we can write nn as x1 minus x, x2 minus x, go up to xn minus 1 minus x divided by x1 minus xn, go up to xn minus 1 minus xn. So if you use this Lagrangian interpolation formula for our problem, this is the r bar where x1 equals to 0, x2 equals to L, and this is the coordinate system where x is going and total length is Le. So this will be Le. Now our n1 will become x2 minus x upon Le. So if you write this, x2 is itself Le, so Le minus xCl upon E, then it will go 1 upon x minus Le. Similarly, n2 is minus x by minus L, which will become x by L. So if you see the options, you will get the correct answer as D. Let's go to the fourth question. So what fourth question says, it's a simple theoretical question. We can directly answer it. So we know that for this Bubnov-Glarkin, V is phi, and for Petrov-Glarkin, it is not correct. So answer is A. Now question number fifth, it says choose the correct option. The first is Glarkin method requires higher differentiability than Rayleigh method. And another statement says, unlike Glarkin method, differentiability is transferred in weight function through a integration by parts in case of Rayleigh. So let's to answer this, let's assume a basic differential equation which you all know as this. So here what we see, u is second order differentiable. Now to solve it, we'll make it a weak form. How we do it? We make it 0 to 1, then weighted function multiplied by the residual plus q, and this dx equals to 0. So when you use a integration by parts, what you will get? You will get v e a du by dx 0 to L minus 0 to L dv by dx e a du by dx. I'm just applying the integration by parts formula. Dx plus 0 to L, here should be L, v q dx, and this is equals to 0. Now what you observe here, so you can observe here that this v and this two are having first order differential. So what we observe, we can write it as in RR method, which is Rayleigh method, differentiability is transferred. What got 2 minutes late in submitting week 2 assignment on 12 emails sent but rebound. I don't know about that. You have to contact them. In Lilith method, differentiability is transferred uh, in weak form through integration by parts, which we have seen. Whereas in Glarkin method, whereas uh, Glarkin method does not require integration by parts, thus higher differentiability. Which we have discussed here. So the option A is correct, which says both are correct. I hope you all are getting it. Now question number 6, if we see, there is a differential equation given, and it is ranging from 0 to 1. It is said that consider pqf as the unknown function of x and phi as the field variable. V is your weight function, and you have the weighted residual statement we have to verify. So what we'll do, first we'll write the differential equation which is given. Okay, so this is the differential equation which is given. Let's find the residual of it. This is the residual. Now to find the weight function, means weak form, what you do, you integrate this from the limits and do v of r, which is p d2 phi by dx square plus q d phi by dx plus phi minus f of dx equals to 0. This is how we make a weak form, and when we solve it, we don't need to solve it, we just have to write the answer in the weak form equation. So 0 to 1, then vp d2 phi by dx square, it is given in terms of this only. Okay, so then plus vq d phi by dx plus v phi is whole to dx, and also we can write in RHS as 0 to f vf dx. So which is the correct option? If you find it, the option is B. Okay, so question number 7, let's start. So as your query was, yes, the 7th, 8th, 9th and 10th, the answers are not there, means the question is wrong. But still I'll solve for this question and show you the solution how it is done. So u bar is given as c1 phi 1 plus phi naught. Okay, so where phi naught is 1 minus x and phi 1 is x minus x square, r is equal to r is the residual, which will be d2u by dx square plus u minus 2. So now what you have to do, you have to find the weight function. So for that, let's find the residual. So we can write here in two ways we can write here. Let's do it in terms of phi only. So we can write r is equal to c1 d2 phi by dx square, which we are putting in from there, and plus d2 phi by dx square, which will be phi naught. This is phi 1, this is phi naught, and then we can write c1 phi 1 plus phi naught minus 2. This is u1 which here I have written. Okay, so this is over. Now what you have this residual value. Now we can substitute the value of phi and all. So let's compute the values which are inbuilt in it. So phi naught we know is 1 minus x, and phi 1 we know is x minus x square. So we can do d phi by phi naught by dx, which will get minus 1, and d phi 1 by dx, which will get 1 minus 2x. Similarly, since we are using two differential second order differential as well, we can write d2 phi by dx square equals to 0, and this is not, and d2 phi 1 by dx square equals to minus 2. So when you substitute in this r value, what you will get? This will be c1 minus 2 plus 0 plus c1 x minus x square plus 1 minus x minus 2, and you solve it, you will get minus 2c1 plus c1x plus minus c1 x square plus 1 minus x minus 2. Okay, so for v, we from the least square method we know it's dr by dc1. So when you will do this, you will get minus 2 plus x minus x square, which you can't see in the option. So the correct answer is this for v, but it's not present in the options. So this 8th, 9th, 10th, the similar questions I have solved in the previous classes. So I won't solve it again because the answers are still not correct. So no need. for that. So the second part of this lecture, what I'll cover the questions which were asked in the last class. So let's start with that. So the first doubt which was, I'll mark as in doubts. The first class. Okay. So first doubt was in the question number 4 of assignment number. I think it was 2 because I'm third. Okay, 2. So where it was given as d2u by dx square plus u square plus x cube equals to 0 for this statement, and u was 0 at x is equal to 0, and du by dx is equal to 1 at x is equals to 1. So we have to find the weak form equation. So what we did, we solved like this, and for this okay, the question it was given as 1, but it should be L here. I'll repeat, it should be L here. Okay, so for 0 to L we are doing it. We'll write the integration. We'll say the residue is d2u by dx square plus u square plus x cube dx. Now when you open it, you'll get 0 to L v d2u dx square dx plus 0 to L v u square dx plus 0 to L v x cube dx. I'm just multiplying v with all the terms. Now what you have to do, you have to do a integration by parts of this so that the differentiability of u can be reduced. So how to reduce it? I'll do the integration by parts. So I'll get v du by dx from 0 to L minus 0 to L dv by dx du by dx plus 0 to L u v square dx plus 0 to L v x cube dx. So the this boundary term will become v du by dx whole at x is equal to L minus v du by dx at x is equal to 0. So from boundary condition which is given, this one at x is equal to 1, this should be x is equal to L. So it will become, this will become VL minus, now the doubt was this, how this term is getting cancelled. So it will give v0 of du by dx at x is equal to 0. So we see there is no condition of du by dx at x is equal to 0, but we know that weight function should satisfy the homogeneous boundary condition. So since u0 at x is equal to 0 is the boundary condition, so homogeneous boundary condition will be v0 equals to 0 at x is equal to 0. So this term will cancel out due to v is equal to 0. So this I discussed the last time also. So this is the correct answer. So is it clear right now? I hope
Yeah.
it is clear. Okay. So so next question was how this equation is valid, means Doubt number 2, I'll write how the potential energy equation is valid, which is pi is equal to strain energy minus work done, external work done. Okay, so I'll start from the basic. Let us take a coordinate system, y, z, x, and let's take a body, and some traction forces are acting on it. Some body forces are acting on it, and there let it be a one point load as well. So what you will write as work done in external, you will write half. Let it be a linear elastic body, so you will use half here. So in volume you will write u bar transpose b, which is the b vector of now the body forces, plus half of surface u bar t into traction into ds plus summation of ui transpose into pi. So what I have written here, this is force into displacement only, force into displacement only, force into displacement only. Since b is a vector and it's distributed on full volume, so a volume integral is being done. Traction is distributed on a surface, so surface integral is applied, and point load is acting on a point, so a summation is required here. So from this you can get the total external energy of a body. Now to calculate the ue, which is potential energy, is external potential energy, this will be equals to minus of work done of external. Now similarly, now you have to calculate the internal energy, internal potential energy. So what it will be? It will be half due to elastic linear elastic material and sigma transpose epsilon dV. So the external work done is calculated on the basis of forces we are applying. The internal potential energy is calculated on the basis of internal forces which are observed in the material due to the applied loading. So these are the two differences. Now if you want to calculate internal work done, that will be equals to minus of ui. So now you have two terms, one is external work done, one is external potential energy, one is uh, internal work done and internal potential energy. These two are related by a minus sign both. Now we have to get other equations, what how the that formula came. So there is a principle of virtual work, which says a deformable system is in equilibrium if sum of external virtual work and internal virtual work is zero. For virtual displacement, let it be delta ui. So I hope you all are familiar with this principle. So what it is saying, it is a way to relate these internal and this internal and external work done So how it is related? It says delta of Wi plus delta of We equals to 0. Now we have calculated delta dwi also, and we know how what is the formula of We as well. So we can substitute in this, and we'll get delta of epsilon transpose sigma dv minus volume integrals of half delta u transpose b dv minus delta of u transpose on surface, then traction vector ds minus summation of delta ui pi equals to 0. So what I have done, I have just substituted, this is the internal potential energy and this is external work done. Okay, now let's now one more to get the correct formula like this, we have to understand one more principle, which is principle of stationary potential energy. Okay, so can anyone tell me about this principle of stationary potential energy? So I'll explain this as well. So actual deformation, you're telling something?
No, I mean, what exactly is the stationary potential energy?
This is the principle of stationary potential energy. What it defines is actual deformation corresponds to equilibrium for which total potential energy assumes a stationary value. Is it fine or should I explain this? Any system,
Yeah.
any system
Yeah.
is in equilibrium only when the potential energy of the system is minimum.
Okay.
Okay, so this is the potential energy principle. So if you see the top one, this is the
Yeah.
the top one, the LHS is total potential of a body. So what
Yes.
we can write, we can get the delta bar and we can write delta pi equals to 0, where pi is equal to strain energy minus work done external.
Okay. Okay.
So you
Understood.
will get this equation proved.
Okay.
So I hope the person who has the doubt in this and can see the video and get it.
Yeah.
So another doubt was that the third doubt. He said that y tilde equals to yx epsilon this. So how to visualize this? The question was how to visualize this statement. Okay, so in this problem, this is a small parameter, and this has a condition that eta at x1 equals to eta at x2 equals to 0. So let's say we have a graph like this, and this is x, this is y, and so at some x1, at some x2 which is bounded by this is your yx, this is your yx. Now what you have to do, you have to find a optimum solution between optimum function from x1 to x2. What you will do, you let's say you have this arbitrary function as this. Let's say it is like this. So now using this eta, you can perturb this function. See, when you'll add this yx with this function using a small value of eta, you will get this function and you can have a new path. Similarly, when you vary eta more, you can get this path. Here I am taking a simplest neta value, as it is changing here only and rest it is 0. So since it is 0, this path is not changing, only this path is changing. It can this eta we can put negative as well, so we can get this path. A simpler version we can write like this as well. This is y, this is x. Let's say this is fx. Oh, sorry, yx. And this is x2. This is x2. Let's say our neta is this. Now, changing the value which is 0 at this point, 0 at this point. Now, when you perturb with some eta, you will get a same curve like this, or you can get like this. Can you get this? Is it okay?
Yeah.
Okay. So what we can write? For given neta, we can generate infinite number of paths by changing epsilon. I hope this statement is clear. So
Yes.
I'll move forward. So for any neta x, y tilde x coincides with extremizing path if epsilon equals to 0. So we'll extremize the problem, and since we know yx is the optimum solution, which we don't know but we'll have to find it, so in the end we can put epsilon is equal to 0 to get the optimum path as yx. So this was the doubt asked in the last class. I hope the picture what is happening in this problem is can be visualized. So after this, what we do, we extremize the problem. So this was the doubt number 3. I'll ask write the doubt number 4. Why extremizing by differentiating in terms of epsilon? Okay, so we have seen that what problem we are solving. We are extremizing x1 to x2 f of x y y dash dx. Okay, so since we are taking a perturb section where y tilde is y plus epsilon neta, and y dash will be y dash plus epsilon neta dash. Now to write I neta, we'll write it as x1 to x2 f of x y tilde and y dash tilde to dx. Now when we'll put the values, it will form x1 to x2 f of x1 y plus eta neta plus y dash plus eta neta dash dx. Okay, so now what main thing is to observe here is I is a function of epsilon. What we are doing, we have a function we have a function, we are perturbing it with a different function, and we are changing this function using the value of epsilon. So with this epsilon we can get this, with a smaller epsilon we can get this, with bigger epsilon we can get this. So we can get each of this curve, how these 2 points can be connected. So now our functional is only a dependent of epsilon. So that's why to solve this, what we do d by d epsilon at epsilon equals to 0. This is the same problem which we solve when we do dy by dx equals to 0 at certain x, and we get the value of x, and we put in the second derivative to get the whether it is extremum or the maximum or the minimum. So the one more doubt someone asked, that how Taylor series is valid for functional. So simple answer for this is this, that Taylor series is valid for everything. Means for any function you see, let it be sine x, cos x, is the trigonometric function, we know e power x, other all functions we see, whether it's a function or a functional itself is a function, so it also should follow the Taylor series expansion as well. Okay, so I think these were all the only doubts which were asked. Do anyone is having more doubts? I'll wait for 5 more minutes to start the new solutions. If you have the doubts, you can ask.
I don't have.
Okay, you don't have. So okay, I'll start with the solutions of the which are related for the next assignment. So this is the cosine function. Uh, you have to guess which class m function is there, which is the m. So before this, I'll give you a theory a little bit. Can you tell me what is the meaning of cm function?
This is the exponent.
No, this is not the exponent. I say the function, let us say x square. X square
Okay.
is cm function. What does it mean?
No idea.
No idea. Okay, no problem. So cm function signifies that m derivatives of this function is continuous. Okay, so let's say we have okay, so here it is given cos x, so we'll write cos x as fx. So we have to check how many times its derivative is continuous, so we'll write f dash x, which is minus sin x. Is sin x continuous? Tell me, is sin x
Yeah,
continuous?
yeah.
Yeah, simply. Now again,
Yes.
let's do a differentiation. It will give you minus of cos x. Is cos x
Correct.
differentiable? Continuous?
Yes. Again,
Yeah.
it is.
So it how many? It doesn't matter how many times you do a differentiation of this. It will again give you cos x sin x cos x sin x, which is always continuous.
Yeah, it's all. It's an infinite loop.
Infinite loop. So what you can say, this is a C infinite function.
Okay, got it. It's very clear now.
Uh, so let's take one more example. What about you can say about this mod x? So this is x, this is y, this is the graph of mod x. Now tell me,
Yeah, this is also continuous. It keeps going.
No, no. So you have to check how it is continuous, how much many times it is continuous. So what you will write, fx equals to x for when it will be positive x for x greater than 0. We can distribute like this. Is it fine?
Yeah.
Okay. Now let's do a first derivative. F dash x equals to plus 1 minus 1 or x positive x negative. Is it okay? Clear?
Yeah.
So is it continuous?
No.
No. When you plot the graph, what you'll see, it is coming like this.
Yes.
It is coming like this. So it is not continuous.
Correct.
So what's C not function? CM function will be?
It will be one.
No, it is not continuous at 1. So it will be
Okay.
C not function. So
Okay.
the minimum it is no, continuous. It is a continuous C that function. So this is not continuous. You won't give it as C1. You will get C
Okay.
naught function. So whoever asks you whether mod x is which C naught or C1 function, it's a C naught function.
Okay.
So this is a different problem. Okay. So read this a little bit. I'll explain about this as well. I'll answer before this. I'll answer two more doubts which were asked in the email. One was this. I remember one person asked. One person asked. This is the doubt number 6. Why we need to do integration by parts twice for beam. Okay, so I'll start with it. Let's say this is our beam equation. Okay, so we'll start finding a weak form which will be 0 to L W. We do a integration by parts with this, and we'll get W E I dq by dx cube for 0 to L minus 0 to L ei d3v by dx cube dw by dx of dx. Now again we do a by parts of this, and what we'll get, minus dw by dx ei d2v by dx square for 0 to L plus whatever integration we have. Now you see, we observe in axial problem you have a 2 order of this equation. Now you have a 4 order of this equation. So you require 4 boundary condition, and that too meaningful bounding condition. So you see, when you do a one time by parts, what you'll get, you get a two boundary condition as this as v and dv by dx, and from here you will get 2 as ei d3v by dx cube and ei d2v by dx square. So do you know how I have written these 4 boundary conditions from this? Is it clear, or I should explain?
No, it's clear.
It's clear. Okay. So so these two are essential boundary condition, and these two are natural boundary condition. So this is giving you moment. This is showing you moment. This is showing you shear force. This is showing you slope, and this is displacement. So since it is four order problem, so we do different integration by part until we get four meaningful boundary condition. That's it. Okay. So he asked one more question. Huh. So this was question doubt number 6. Let's answer doubt number 7 as well. He asked uh, how to know that at what approximation we are getting the exact solution. Okay. So let's say okay, let's say we assume U as C151. In this case, the let mm, okay, let's say the correct answer is C151, C252 plus C353 plus C454. So this the correct solution have four fives, and in that you can get the correct solution of u. So when you assume it as u1 as c151, you will not get a correct solution. To make it correct, what you will do, you will increase the number of elements, number of terms, c252. Okay, since it is still not matching, you can go again and go to C151 plus C252 plus C353 plus first you go like this 53. Let's directly move to fourth one. So in this case, you will get a correct solution, but you don't know is this a correct solution or not. You make it more element. What you will do, C151, C252 plus C353 plus C454 plus C555. So what you will observe in this, when you cross this limit, which is the exact solution, you will get the extra term constant as 0. So this signifies, since your extra term constant is 0, this means you have reached the correct solution, and this is the correct approximation. You don't have to go into more terms again. So these were the 7 questions. Is this clear?
Yeah, this is clear.
Okay. So let's start with this. In a beam problem, so I'll explain a bit little about the Newman and the Dirichlet boundary condition before going through this question. So when we write a weak form, which is 0 to 1 W, let's say a axial bar problem only. This is the axial bar problem. We'll write a weak form as dw by dx du by dx minus wf dx minus w du by dx 0 to 1 equals to 0. This is the weak form we have written. Now let me define what do you mean by natural Newman or Newman boundary condition. So what definition says is coefficient of weight function and its derivative in boundary term. are known as secondary variables and correspond to NBC. So do you understand what I have written here? Have you seen this line anywhere?
Percent of weight function is no. I didn't get it.
Okay, so I'll explain. So boundary conditions are defined by this boundary term. Okay, so in
Yeah.
any problem, this is a simple problem. You know what is your boundary condition, what is your Newman, what is your Dirichlet. But any problem you are solving, you will get a boundary term like this.
Correct.
So what it is saying, new coefficient of weight function and its derivative in boundary term. This is the boundary term.
Okay.
The coefficient of weight function. What is the coefficient of weight function? It is du by dx.
Yeah.
Is there a derivative also in this boundary term?
Yes.
No, derivative of weight function. Is it there?
No, no.
No.
No, no.
If
In
it
this we
if
don't
it
have.
had been like this, na,
Yeah.
something like this. Maybe it is let us assume like this. Then one more will come up as u if
Okay.
this is available. So this coefficient also will correspond to Newman boundary condition. Since here
Okay.
we are having only du by dx, so du by dx is our Newman boundary condition, and this variable will be known as secondary variable. So since you know in axial problem what is your Newman boundary condition, what is your Dirichlet boundary condition, you can directly see and write. But in general problem, you don't know what is the boundary condition. So this is
Yeah.
the criteria how you have to check. Similarly, I'll
Okay.
talk about the essential boundary condition as well. Essential or Dirichlet boundary condition. So what a definition say? Weight function appearing in boundary term boundary, uh, weight function in the form of unknown variable, means which is u, what we say as uh, unknown variable is known as primary variable, and boundary condition corresponding to it is known as essential boundary condition. Now read this and let me know if you understand, otherwise I'll explain as well. It is a little tricky. So it says weight function appearing in boundary term in the form of unknown variable. So weight function is this. How it is appearing? A single variable in the form of u, in the form of unknown variable it will be u. So here u is the essential boundary condition. Let's say the weight function is like this in this boundary term. So what will be your extra EBC? It will be du by dx. Did you get that?
Yeah.
So now this along with the boundary conditions as essential and the natural, you can tell what are the primary variables, what are the secondary variables.
Yeah.
Uh, Okay, so now let's get back to this problem. In a beam problem, if displacements are known at both ends, then it says displacement at both ends will be referred to as natural boundary condition. Other says displacement at both ends must be homogeneous to solve the problem. The C part said displacement at both ends will be referred to as essential boundary condition. So we know the it is the displacement as essential boundary condition. I have done it for axial bar. If you do it for beam, you will get it same as like this. C. So answer is C. So a similar problem related to this is this. Just read it. So it says in a beam problem, if bending moments are known at both ends, then okay. So it says bending moment at both ends will be referred to as natural boundary condition. Bending moments at both ends will be homogeneous to solve the problem. Bending moments at both ends will refer to essential boundary condition. So when you solve the beam problem and you get to know this primary and secondary well, you will get to know that bending moments at both ends are referred to as natural boundary conditions, which are the secondary variable for this problem. So let's see question number 5. This is a simple one. Which of the following is not true about Timoshenko beam? Primary variables are displacement and slope. Secondary variables are shear force and bending moment. And cross sections which are normal and plane to longitudinal axis remains normal and plane it after bending of the beam. So do you know what is the difference between the Euler-Bernoulli and the Timoshenko beam?
Yeah, plane sections
Correct.
remains plane.
So
Oh,
this is not correct. This
yeah.
assumption is not valid for Timoshenko beam. So why I put this problem here? So you see that these two options are same for that. A and B are valid for Euler-Bernoulli beam also and Timoshenko beam as well. So you see
Okay.
that primary and secondary variables are not changing according to the beam, but the major assumption has been changed. Okay, so this is the question now related to the frequency thing. Some of the questions you will get in the assignment as well. So let's do this problem. So the question says, suppose we are interested to find fifth natural frequency of a cantilever beam. Okay, the beam is analyzed using Euler-Bernoulli assumption. Okay, no problem. And two node element with Hermite cubic interpolation is used. So how many minimum elements are required to capture fifth natural frequency? So have you gone through the lectures of this week?
Is it fourth week or fifth week?
Fourth week.
Fourth week. Yeah, partial.
Partial. So the faculty has discussed some of the things of how to get the frequency of the structure or beam of this game. So this is this type he has not discussed. So now you have to let us assume a cantilever beam like this. So one node, two node, three node, four node, or let's say it's n node. For a beam, this will be degree of freedom, this will be degree of freedom, this will be this, 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 and at n also it will be like this. So now you have n elements here. This is 1, 2, 3, and it go up to n elements. For n elements, you know we need n plus 1 nodes. Since we have n plus node, how many degree of freedoms will we have? We have 2 of n plus 1.
Yeah.
Okay. So we have 2n plus 2 degree of freedoms in this structure. Now, when you form a global stiffness matrix, you will get it as the dimension as 2n plus 2 cross 2n plus 2. Is it fine?
Yeah.
Okay, so now you have to, for solving this, we know that before when we write a global stiffness matrix, it is singular, so you can't find the solution right away. You have to reduce this stiffness matrix to get the solution.
Yes.
So since here no, there is no horizontal force, we can reduce 2. We can reduce 2 degree of freedoms, which is RBM. So you will, what you will write, your reduced K will be of dimension 2n plus 2 minus 2, 2n plus 2 minus 2. This will come 2n cross 2n. Is it fine?
Yeah.
Now to solve this problem, what you will get, you will get 2n eigenvalues from this. And for solving the frequency, we know if you want fifth natural frequency, we should have 5 eigenvalues. So 2n should be greater than 5, which is n should be greater than 2.5. So n minimum required is 3.
Yeah.
Did you get this concept?
Yes. Yes.
Okay, so the answer is 3. Let's go to the next question. I'll ask you one more question related to this also. What if one element was 3 noded? Each element is 3 noded. Means this is your one element and you have 1, 2, 3, like this. Can you guess something?
Yeah. We need one,
Now
two, three.
similar thing we will do. Let us see elements. We are having one element, so how many nodes we are having? We are having 3.
3 nodes.
Let us see, we are having 2 elements. How many nodes we are having? 5. Similarly, if we increase this as 3, we'll have 6, 7. So for 3 element we have 7 nodes. Is it
Yeah.
fine? Similar trend if you form, for n elements we will have 2n plus 1 nodes. Since we were able to find here directly how many nodes are there, we just have to see a trend in this and we get to know that 2n plus 1 nodes are present for if we make a 3 noded element for this problem. So if we see
Yeah.
the degree of freedoms, it will be twice of 2n plus 1. Similarly, global K will be twice of 2n plus 1 cross twice of 2n plus 1, which is 4n plus 2 cross 4n plus 2. Now if you reduce it, reduce K will give you 4n cross 4n. Now to get, you will have 4n eigenvalues. If you want more than 5 natural frequencies or 5 natural frequencies, this should satisfy and n should be greater than 5 by 4, which is 1.25. And we can say if we want n minimum is 2. So if we are using a 3 noded element, if we want a 5 natural frequency, minimum 2 elements are needed. Okay, so this question is the question number 7. This will be very helpful for solving the problem on the assignment. So let's read what it says. Natural vibration of a beam under applied axial load P naught is governed by following differential equation. Okay. Identify the proper weak form of the differential equation. You have to find it. And boundary forces are Qi. Slope is given. Integration is carried out. Given and weak form is this. Okay. So let's start solving this question. So you have to find a weak form. Again, I have done too many questions from before to form a weak form. Just let me know how to start. How should we approach to a problem of differential equation to form a weak form?
Now, first we'll bring everything on one side and make it equal to zero, and then
No, equal
put
not
the
equal to zero. Equal to zero. Then this will be a
yeah,
residue. When we'll put this,
yes, residue.
this
Then multiply that with an weight function.
correct, correct. Okay, so I'll start solving it. So let V be the weight function. So I'll start 0 to L V d2 by dx square ei d2w by dx square plus it's p naught. So we can do this as, this as bigger one, p d2 w by dx square minus rho a w square. Oh, this is omega square and this is w. I'll write it capital W to avoid confusion. Dx. Okay, so this will be equal to 0. Now what they want to solve as the equation as well. So let us take this as let's do the integration by part of this. And if you do it 2 times, I'll directly write it what you will get. d2v by dx square ei d2w by dx square dx plus some boundary terms in this. And we need to do a by parts here also. So p naught d2w by dx square will become minus of 0 to L dv by dx p naught dw by dx plus some boundary terms. So the RHS, let's take it into the RHS, which is 0 to L. Rho is, this is w dx. So let's see which it is solving. The answer will be A, which is matching the solution. Okay, the boundary terms are just the simple terms which we'll get after solving. I have solved too many times. I know you can do it like. Okay, so this is a little bigger problem. We have to read it properly, then start. So what it is saying, consider the following propped cantilever beam with an overhang and answer the linked question from 8 to 10. Okay, so this we have to see that this is a propped cantilever beam. A beam is disguised with two elements of equal length. Beam is having constant EI, unit mass m throughout. The nodes and corresponding degrees of freedom are shown in the figure. Analyze the beam for identifying the fundamental natural frequency. Okay, and the question says, in order to find the natural frequency, the elemental mass and stiffness metrics are calculated, assembled to global mass and stiffness metrics. Oh, so it's giving you the hint how to solve it. Next, the whole system or equation is partitioned corresponding to unknown degree of freedom and unknown generalized degree of freedom. This identify the equilibrium equation to use for find this. Okay, so let's start solving this. So I'll take the mass matrix which is already covered in the class. For that you have to see that class how it came. It generally comes by n transpose n dx, something like this. So you have to see that class how it come. So directly I use that matrix which is rho e he by 420, and it is 156 minus 22 he and 54 and 13 he. Then it will come 4 he whole square minus 13 he minus 3 he whole square, 22 he, 4 he, 156. So this is the generalized mass matrix you get for this Euler-Bernoulli beam. So for element, let's say 1, which is this let it be 1, this is be 2, but all are same length, so 1 and 2 will have a same properties. So let's write for 1, the m will be rho e ae, which is equals to m, which is given in the problem like this, rho a. Now le will be l by 2, so he we are using here, so he will be l by 2. Now you write mass matrix for 1, first element. So degree of freedoms for first will be, means this will be 1 2 3 4, this already given here. So 1 2 3 4, so we can write 1 2 3 4 corresponding 1 2 3 4. So we know this is the mass matrix, so when we'll substitute in this will be ml by 840. So what we are doing, we are substituting all this value in this and getting the elemental mass matrix for element 1. So this will be 156, it will not change. This is 11l, this is 54, then 13 by 2l, then l square minus 13 by 2l minus 3 by 4l square, then 11l, then l square, and 156. Just if when you substitute, you will get this. Similarly, we have to find the elemental matrix for element 2 as well. So what will be for m element for element 2? So properties are same, so we can use the similar properties to substitute in this for the second element as well. Just what will be changed, the degree of freedoms corresponding to this element. So here it is 3 4 5 and 6. So 3 4 5 6 should come here, which is 3 4 5 6. Here also 3 4 5 6. Now what we'll do, we'll start substituting again in this, and what you will get is ml by you will get a same thing, means same like me1, just these things are changed. So now you have to form the global m, which will correspond to 1 2 3 4 5 6, 1 2 3 4 5 6. So so you know how to get from global stiffness matrix from elemental matrix.
Yeah.
Okay, so what you will do, you will just add the corresponding elements in this matrix to get the full global matrix. So the solution what you will get is 156 minus 11l 54. I'm writing it directly, you can directly solve it, or you have a same problem in assignment as well. There you can solve and get to the solution. 1 2 3 4 2 3 4 6 6 7 11L and L square. Then here it is 156 minus 13 by 2L. This will be 0. This is 2L square. Then 3 by 12. I think this is okay. Then this is symmetric about this. So you get this global stiffness matrix. So after this, okay. So what is asked in the question? Okay, we have to write the full equation. So let's find the q vector as well. Q vector is the force vector in ku is equal to f. So this is I'm writing as q. So in dynamic problem we don't have any. In dynamic loading we do not consider extra loads. So for that q is equal to 0 0 0 0 0 0 plus the static loads which are q1 q2 q3 q4 q5 and q6. These are the general loading we have seen in our previous problems of FEM, and we will use that. So in this problem if you see, q1 and q2 are unknown because they are the reactions. q3 is unknown, but you know q4 is 0, q5 is 0, q6 is 0. Is it okay?
Yeah,
Okay.
it is
So
correct.
this is 0, this is 0, this is 0. So our equation will form k minus omega square m equals to q. So k we have written, we'll multiply the omega square with the m matrix and you will get the, we have written the q matrix as well. So now what they have given, they have given u4 u5 and u6. Okay, so here one u matrix will also come as qu is equal to f. So here it will be minus omega square m with u1 u2 u3 u4 u5 and u6 and corresponds to q full vector. Now we know with this u1 is 0, u2 is 0, u3 is 0. You can put this as 0 and this 0, this 0. So what you will get, a reduced matrix of this, and here it will be u4 u5 u6 and q4 q5 and q6 which are 0, which are already 0. So there it will be 0 0 0. So if you will solve it, so since I have given you the values, the k matrix is same as the Euler-Bernoulli what you get, and the solution which will you get is B. So if you see this 156 is there in our solution, this is there. What is the difference in this? These are two same, but is different in this is 840. So what we are getting? Oh, I have not written it full, but it will get a 840 thing. So this is your solution. Now let's see what other things are asked in this. What will be the governing differential equation? Governing equation to find natural frequency. Phi. Okay, now what you have to do, you have to, since you know you have this k omega square m, this equation. U equal to Q, and you're solving a reduced K matrix, not the K matrix, we can directly write reduced K minus omega square M matrix we got. Now he's saying to get the governing equation to find the natural frequency, and it is giving a hint is also that take determinant of the left side of previous question. So for finding the natural frequency we have to get the eigenvalues of it. To get the eigenvalues, what you have to do, we have to do a determinant of k omega square m and put it as 0. When you will put it as 0, this will give you a characteristic equation, and if you solve it, the option will be, I'll give the answer beforehand, which is D. So this will be the answer. I hope you know what is eigenvalue problem and the characteristic equation. Is it fine?
A minus lambda x.
Sure. Just you have to write that, and you will get the equation like this. Okay. So the same related question is there, that you have to find the fundamental frequency. So the highest one, the eigenvalues will be the fundamental frequency, and this will be the a part in if you solve this. So that's all I have for today's class. If you have any general query or anything to ask, you can ask. If not today, I will discuss it in the next class as well. Anything from today's class also you can ask.
I think it's clear.
It's clear. Was the class okay? Means
Yeah, it was very good.
thanks for joining. Otherwise, I don't think anyone else has joined.
It was good. All my queries are answered.
So this last question I haven't solved, but the same question is given in your assignment.
Okay, I saw.
Either you can solve it also, or you can go for the problem given in the assignment.
Okay.
Okay.
Sure. Thanks, sir. Thank you for your time.
So are you getting the mails from the that discussion forum?
Yeah.
You're not getting it. Okay. So anything you can post it there as well,
Sure.
and try to attend the classes of the regular lecture, so that you can
Yeah.
get the better
I
understanding.
don't miss these classes.
No problem. That's good.
Yeah.
Thanks a lot.
Thank you, sir. Have a nice weekend.
Okay. You too. I'll wait if anyone is coming. Thank you. This was the week 4 class conducted on 5th February 2025. My name is Nikhil Gupta. I'm a research scholar at Department of Civil Engineering in ISC Bangalore. Thank you for attending.